Hello guys, today we will implement a model in Python, and in the previous lecture we have gone through with some text mining examples, and we had discussed what is pipelines in machine learning and why we do feature engineering. And feature engineering has a very important role in, especially when we do text mining. So in the text mining, we have gone through with term frequency, and then we realized that the term frequency is not enough to give sense. Um, Instead of counting just the words and then the number of words will give some meaning, uh, we have come across that this is not enough. So it's not necessary that if a word comes once in the document uh, and another word has more counts, and we can say that the other words is important. No, it's not the case. So we have devised another techniques, TF-IDF. We haven't devised that technique, but it's already there. But we discovered that there is a technique that give another features to words uh, instead of number of counts. It gives weight to the words. And there was some mathematical expression uh, which is term frequency multiplied by log and the number of documents divided by a number of words in the entire documents. So today lecture basically it is about uh, how to implement the model in Python, especially in Anaconda environment, Jupyter notebook, and how to extract, get the data, the benchmark data set that is available on the internet. And one of the repository is known as Kaggle, but there are some others as well. So you have to search. Um, we will implement the model and then we will evaluate it, and we will apply our knowledge that we have gained in previous 3 lectures to understand practically those things. So the scenario is that a beautiful lady botanist have collected some flowers, and now she wanted to know that to which type these flowers belong to. And she measured the newly collected flowers, length and width of the petals and length and width of the sepal. So we have a data set that is collected by some experts, and they divided the iris flowers into 3 species: Setosa, versicolor, or Virginica. So and Virginica. So there are 3 classes. The classes are made by their size, the petal and sepal size. So the model will be trained on those data set, and the lady who collected the flower and measured some of the attributes of those flowers will be given to the model, and the model will predict that to which that flower to which class that flower belongs to. And then we will not blindly trust on our model, we will evaluate the model as well. So our goal is to build a machine learning model that can learn from the measurements of these irises, excuse me, whose species is known, so that we can predict the species for a new irises. Okay, so first of all, we can load it by calling the load iris function. So you can see there is, and this is actually Python code from sklearn.datasets import load iris. So this is a library sklearn, and sklearn has many datasets. So we are importing one of the dataset known as iris. So we are going to load iris data. Once we load that, we will put it in an object iris. Iris is an object, so iris has all the data, and iris has also some other attributes as well. Iris.keys means shows uh, uh, the keys, the head, you can say the column heads like data and target, the feature names, etc. All right, so how about if we copy those and put it in our Anaconda slide? Where is our Anaconda? I think it is here. Yeah, we have included some libraries, and here are here is data we are going to load, and the keys. The iris is our dictionary. So there are keys, data, target, frame, target name, description, feature name, and file names. And if I print iris, this one, if I print it here, so I want to see what is inside. So inside this we have some numbers: 5.1, 3.1, 1.4, 0.2. What are these? This is actually the length and width of the sepal. The first one, length and width of the sepals, and the last two are length and width of the petals for the flower number 1. And then we have flower number 2, flower number 3, and so on. We have a lot of data here. um, so I'm now going to use iris keys, and we will see the target names. What are the target names in the dictionary? The iris and the key enclosed in uh, sorry, target names enclosed in what is called anyway. So we have those target of classes: Setosa, Versicolor, and Virginica. And next we have the features name and iris data type, and then we are interested in the shape, and then we are interested in the target shape. Let's do this one by one and see. So feature names in sepal length in centimeter, sepal width in centimeter, petal length in centimeter, and petal width in centimeter. So um, the length and width are given in centimeters. Let's see what is the, it is type of Iris data. It is NumPy array. And now the shape. The shape means how many number of rows and columns. So this shows that we have 150 rows and 4 columns. You know, 4 columns here. Here you can see. So column number 1, column number 2, column number 3, and column number 4. So these are 4, and these are columns. Okay, and this is the number of rows. So how many rows are there? There are 150 rows. It shows 150 rows and 4 columns. So Iris data has 150 entries, 150 instances. And let's see that how many target shapes. So target means the label or classes. So how many uh, instances we have in Iris dataset? 150. So the label would be 150, I guess. Yes. So there are 150 flowers, and each flower has been assigned a label. So both have the same number. Here, what is this? This shows that we are we want to see 1, 2, 3, 4, and 5. We want to see the first 5 data. We want to see. How about if we change it, then you see 1, 2, 3, 4, 5, 6. So we have extracted 6 instances. And let's see the target. The target is in 0, 1, 2. These are some numbers. Why these are in 0, 1, 2? Do you know what are the labels? There are 3 labels. Okay, 3 labels, which were namely Setosa, Versicolor, and Virginica. So there are 3 classes in the data set. But you know, uh, computer executes number very quickly, so we gave them the code. So Setosa has the code 0, Versicolor has the code 1, and Virginica has the code 2. So it says that the target has 3 labels, 0, 1, and 2. Another thing if you note here is that these are in a sequence, these are in order. So the first, how many, just count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So 22, 24, so 22 and 44, 45, 46, 47, 48, 49, 50. So the first 50 are one label, and the next 50 belongs to another class, uh, and the last 50 belong to Virginica. So this means that our data is in order. And now see this here we are importing train split, train test split library. This has a built-in function that splits the entire data into 2 train and test. So what is going to split the data, the ARIS data, and the target? So basically, a random seed means that it should randomly it uh, first shuffles those and then divide the data set into two, one in test and another as a train. So it will return X train data in X train, and the test data. And similarly, it also divides the label as well. So if we see that the how much is X train dot shape, sorry, I have to execute this first. So by default, I think by default, it splits data into 75 and 25 ratio. So 75% of data went into X-train and 25% data went to X-test. So now how many, we can see the shape of X-train, it shows that there are 112 columns. And how many number of columns in test? These are 38. So you guys just do some exercise and find out that how much this ratio is. So next, what is doing? All right, let's go back to our slides, and we should continue the slides as well. When we come back, disco in a minute. This is what we have done. We know how to load. What are the keys? It's a dictionary. It is target name and feature names. Okay, so the target number of rows is 150, and the target is you can see the output is 000, 111, and 222. The meaning of the numbers are given by the arrays. Array 0 means setosa, 1 means versicolor, and 2 means virginica. Training and testing. We need to know whether our model actually works, that is, whether we should trust its prediction. Our model can always simply remember the whole training set and will therefore always predict the correct label for any point in the training set. So when we train our model will perform very good on the trained data because the model already knows what is inside in the training. We have shown them. We have shown our data to our model. So it will obviously will perform good. But how about if we show unseen data to our model, and there we will judge, we will examine that how much our model is generalized, or how much our model is good enough to classify an unseen data. The remembering doesn't indicate to us whether our model will generalize well. So if your model is doing good in on training data set, so still this doesn't show that our model is very good. So before we apply our model to new measurement, we need to know whether we can trust its predictions. So how to assess, how to examine. So this is usually done by splitting the label data we have collected into two parts. The part of the data is used to build our machine learning model and is called the training data or training set. So we before designing our model, we split our data into training and test data. We will train our model on one set, and we will test our model with another one that we have, another data that we have set aside. So yeah, the function x. So it means the default ratio is 75 and 25. 75% data will go to training set, and 25% will go to test set. And now first thing first. So before building a machine learning model, it is often a good idea to inspect the data to see if the task is easily solvable without machine learning. Yeah, the first thing is that before you are going to develop your model, you first see the data by yourself, by your eyes, and see that do we need a model? You can easily predict that what is it. So if you can see, so um, so by examining your data, you can be sure about that which model uh, you can use for this. So additionally, inspecting your data is a good way to find abnormalities and peculiarities. Maybe some of your areas were measured using inches and not centimeters, you know. So you must examine your data set and see that is it all in one scale, or if it is not in one scale, make it to one scale. Like in the second bullet, it says that let's suppose we have some data in centimeter and some are in inches. So first you need to bring those data in some common scale. In the real world, inconsistencies in the data and unexpected measurements are very common. So if there are inconsistencies, your model will not perform good. So one of the best ways to inspect data is to visualize it. One way to do this is by using a scatter plot. So one way is that you just take the data points and put into scatter plot, where you will see that where you can visually see that how much classes are there. Unfortunately, computer screens have only two dimensions. Yeah, so computer screen has two dimensions, so you cannot see uh, three or four or five dimensions plot. So how many features are in our data set? There are four features, four features. Two features relate to sepal and two relate to petal. So there are four features. So we cannot plot uh, so that it can show the four dimensions. So what we are going to do, we will only consider two attributes just to show on just to show on the plot. So here here's the code, and the first thing was that we get handles of our plot. So this shows the figure size should be 1515. So this means that we can change our plot size, and we will get a handle of fig and x, and the subtitle would be Iris uh, pair plot, and there is a loop for I in range 3, for j in range 3, and then we are going to put data from XTrain in scatter plot. C is equal to Y train. C are the labels. S is equal to 60, and then we want a tick at those location AX, IJ. If I is equal to 2, for example, if the label is 2, then it should take that at that location of the plot, and if it is J is equal to 0, then take uh, at that location. So when you execute this code, you will have a scatter plot. So from scatter plot, we can see that the three classes seem to be relatively well separated using the separate petal measurements. This means a machine learning model will likely to be able to learn to separate them. So what is the purpose of this particular slide is that put your data on a scatter plot and then just look at your plot. You will see that there are some clusters like the topmost. You can see the topmost. Um, you have a, you have at top left some black dots, and on the bottom right you have green, and there are some another color as well in the middle. So it shows that there are three different classes. So building our first model, though we haven't um, share this to you. Okay, so this is a scatter plot. Okay, now we are going to build our model. The model we chose is K-neighbor classifier. So this model, the K-neighbor classifier, we will explain it later when we will discuss just K-neighbor class. For the time being, just have a look at how we implement that model. So k-nearest neighbors actually it decide that whether the incoming new plot, uh, the new data when comes, then we'll see that to which cluster it is closed. If it is close to one cluster as compared to the other, then the point will belong to the first one. So it is based on the distance measure. So k-nearest neighbors KN algorithm is arguably the simplest machine learning algorithm. Building the model only consists of storing the training data sets. To make a prediction for a new data point, the algorithm finds the closest data points in the training data set, its nearest neighbors. So closest data points in the training sets. In its simplest version, the algorithm only considers exactly one nearest neighbor. So, for example, let me grab the pen. For example, this is a cross. So it has This data, closest one, it has this data as well. So there are two data close to our, this is our new data. So which, to which this belongs to. So as it is close to the blue, so we will consider this is a class of blue dots. And if you see this point, and there are, this is an unknown point, and we will see the distance of the closest nearest. We will take two nearest points. We will, not 2 points, sorry, just 1 point. So because we are using a simplest nearest neighbor, so in the simplest nearest neighbor, we will use only one neighbor. So which is closest one? Which point is the closest? Let me remove this. So you can see, so the closest point to this cross is red, so this cross belongs to red point. And the closest point to this unknown is the blue. Blue is the closest one, so this is this belongs to blue class. So this is how it works. So let's move further. So this is where the name K comes here. K means how many neighbors you are considering when you are going to decide that to which our new point belongs to, and you are considering the number of neighbors. So here number of neighbors is 1, so the value of K is equal to 1. If you decide the belonging of new numbers to a class based on two neighbors, then the K would be 2. So that's why in the KNN the K comes from. When considering more than one neighbor, we use voting to assign a label. Okay, so we will do, if we are considering more than one neighbors, then the voting will decide that how many votes, like for example, if we are considering 5 neighbors close to unknown number, then we will see that how many neighbors are from blue and how many neighbors are from red. The majority will decide that to which this unknown number will belong in that case. All right, so the mjlearn.plot underscore km classification n underscore neighbor is equal to 3. The n underscore neighbor is equal to 3 means we are deciding on the k here is 3. Again, the prediction is shown as the color of the cross. So look at this. When we have k is equal to 1, when we have k is equal to 1, we got this plot. And when we have k is equal to 3, then see this plot. So let's check that. What is this? We are considering 3. So the closest 3 points is 1, 2, and 3. So this says 2 blues and one red are close to this. As the number of blue is higher, so this unknown class will belong to blue class. While in the previous case when k is equal to 1, it was belonging to red. So as you increase the number of neighbors, it also affects uh, the prediction. And let's let's have a look of this. This was previously belonged to blue. So now see, when it was previously belonging to blue and we have k is equal to 1, and now we change our k, and this time k is equal to 2. So to which this will belong? So k is equal to 3, sorry. So the closest 3 points are this one, and this one. So there are two blues and one red. So to which this unknown point will belong? Obviously to blue, because the number of blue are higher than the red. So when we have k is equal to 3, we have that results. So, so what does this mean? It can be seen that the prediction changed for the points in the top left corner using only one neighbor. And let's use only a single neighbor for now. The k nearest neighbors classification algorithm is implemented in the k nearest neighbors classified in the neighbor module. So we will get the first graph if k is equal to 1, and we will get second plot if k is equal to 3. So if you implement that, if you take that k is equal to 1, you will have the code. So here, see, we are using k neighbor classifier, and we have given k, the number of k here is 1, and we got knn. The knn is the model now. The knn will have all the features of the model. So in the model, we have a feature, we have a function dot fit. You can see the dot fit. The dot fit means apply the model. So knn dot fit, we have given x train data and y train data. X train is the data and y train is the label. So this is where we say that this is a supervised learning, because we are showing that this is the data and that is the output. So learn that. So once we have learned our model, the next is K-neighbor classifier algorithm has some parameters: auto, leaves, size, metric. Uh, the algorithm is auto, leaf size is 30, metric is Minkowski. So when you measure the distance, so which formula are you going to follow when you find the distance? So there are three different uh, way to measure the distance, and one of them is Minkowski. Metric parameters: none, n is equal to job is equal to 1, n underscore neighbors, p is equal to 2, and weights is uniform. So these parameters are explained here. You can go through with this. And now the evaluation parts comes here. We have trained our model on the training data, and now we will take an unknown values and we'll ask our model to predict. So prediction can be made using this model on new data for which we might not know the correct labels. Imagine we found an iris in the wild, means we found iris in some jungle with a sepal length of 5 centimeter and a sepal width of 2.9 centimeter, a petal length of 1 centimeter and petal width of 0.2 centimeter. What species of iris would this be? So we have found an iris with those attributes, and now we are interested in to know that to which species this iris belongs to. Put this idea into a NumPy array. Put this data into NumPy array again with the shape number of samples. Uh, so we put this in NumPy array and then we shape it x underscore new shape, and x underscore new shape means we want to know that what is the shape. Shape is that one row and four columns. And now we are going to predict. So this value is new or unknown, and this is our model trained on the training data. It has a method dot predict. We put x new, and we see the prediction 0. This shows that this belongs to the first label. And if you want to know that what is the name of this one is this shows as Setosa. So our model says that the new flower belongs to Setosa. Evaluation of the model. For just one value, we cannot say that our model is accurate and it has the performance is 100%. So just give one unknown number and the prediction on unknown number is correct wouldn't mean that our model is 100% correct. So we want to an estimation. So that's why we have separated 25% of data, we set it aside, we keep it away, and we haven't shown those data. So now there is a one-line code where we put all the 25 data, the test data, and we will see that how it predicts. And the interesting thing is that we also know the test labels. Okay, so मैं आपको उर्दू में बताता हूँ कि हमने मॉडल को ट्रेन किया, तो अब हम मॉडल को एवेल्यूएट करना चाहते हैं। तो एक वैल्यू देने से वो अगर सही बता दे तो हम नहीं कह सकते कि ये 100% सही है। तो ट्रेनिंग डाटा के शुरू में हमने डाटा को दो हिस्से में तकसीम किया था, 75% ट्रेनिंग के लिए, 25% टेस्ट के लिए। तो 25% हमने अलग रख लिया था और वो हमने नहीं दिखाया मॉडल को सिर्फ ट्रेन डाटा दिखाया। अब एक ऐसा लाइन है जिसमें हम वो 25% डाटा उसे कहेंगे कि इसका बताओ कि क्या है, तो वो मॉडल 25% को एक ही लाइन में बता देगा कि इसमें जो है कितने क्या हैं। हमारे लिए दिलचस्पी की बात ये है कि टेस्ट डाटा के लेबल भी हमारे पास हैं। मतलब कि हमारा मॉडल अगर कहे टेस्ट डाटा पर कि टेस्ट नंबर 1 का टेस्ट डाटा का जो डाटा नंबर 3 है वो इसको बिलोंग करता है, तो हम वेरीफाई भी कर सकते हैं क्योंकि हमारे पास असल लेबल भी मौजूद है। तो वहाँ से हमें पता चलेगा कि ये कितने परसेंट, हम अंदाज़ा लगा सकते हैं कि कितने परसेंट हमारा मॉडल ठीक होगा। तो यहाँ देखिए हमने सारा का सारा एक्स टेस्ट डाटा डाल दिया। एक्स टेस्ट में 25% डाटा है एरिस के डाटा सेट का। उसने वाई प्रेडिक्शन में डाल दिया। वाई प्रेडिक्शन है कि ये हमारे मॉडल ने कहा है कितने हैं, कौन कौन सा है जो क्लास 1 को बिलोंग करता है और कौन से ऐसे हैं जो क्लास 2 को बिलोंग करते हैं और कौन कौन से इंस्टेंसेस ऐसे हैं जो क्लास 3 को बिलोंग करते हैं। तो वाई में हमारे मॉडल की प्रेडिक्शन आ गई और वाई टेस्ट में हमारे पास एक्चुअल लेबल्स पड़े हैं। हमने इनको अब ये numpy डॉट मीन्स हमने निकाला कि देखो ये दोनों को बराबर करके देखते हैं कि कितना इनके ठीक है हमारे साथ, कि वाई प्रेडिक्शन किया और वो वाकई में एक्चुअल वाई टेस्ट के साथ मैच कर रहा है। तो उसका मीन निकाला तो हमारे पास 0.97 आया। इसका मतलब यह है कि हमारा मॉडल 97% ठीक था। तो 97% हमारा मॉडल ने अच्छा काम किया। एक और भी तरीका है कि हम के एन एन डॉट स्कोर करके एक्स टेस्ट का डाटा यहाँ रखें और वाई टेस्ट का डाटा यहाँ रखें, तो ये हमें बता देता है कि ये मॉडल 97% इस पर एक्यूरेट है। ओके गाइस, सो यहाँ तक ये हो गया है। अब हम ज़रा इसको वहाँ जाके चेक करते हैं, एनाकोंडा में जाते हैं और वहाँ इसे चला कर देखते हैं। तो देखें जी, वन नेबर हम ले रहे हैं, एक नेबर, टू नहीं, एक नेबर ले रहे हैं। और यहाँ हमने देखा कि ये वही है कि फिट मॉडल फिट कर रहे हैं और मॉडल के पैरामीटर सेट कर रहे हैं। ये ट्यूनिंग पैरामीटर्स कहलाते हैं, ट्यूनिंग पैरामीटर्स। और यहाँ पर हमने अननोन वैल्यू दी और उसने उसका शेप बनाया, और फिर हमने वो अननोन के एन एन के प्रिडिक्शन को दिया। उसने हमें बताया कि ये क्लास ज़ीरो को बिलोंग करता है। तो हम ज़ीरो की जगह हम ये देखना चाहते हैं कि वो हमें लेबल दे उसका। तो वो क्या है कि सेटोसा है, और ये प्रेडिक्शन किया 97%। इस सब को हम एक लाइन में भी लिख सकते हैं कि के एन एन डॉट स्कोर, मॉडल नेम डॉट स्कोर, और ये एक्स टेस्ट और ये वाई टेस्ट। एक्स टेस्ट टेस्ट में अननाउन डाटा मौजूद है जो कि उस मॉडल के लिए अननाउन है, और हमारे पास उसके लेबल हैं, वो भी हमने यहाँ डाल दिए हैं। अब वो अपने प्रेडिक्ट किए हुए मॉडल और हमारे एक्चुअल मॉडल से कंपेयर करता है, वो बताता है कि ये इतना है। तो ओके गाइस, अब लेक्चर 5 को करते हैं, लेकिन जूम मीटिंग में मैं एक नया मीटिंग की रिकॉर्डिंग करता हूँ।